Hello, my name is Richard Albayaty. I'm a PhD student at the University of Florida, and today I'll be presenting my project on video background subtraction using robust PCA. For any questions or for a list of references or the accompanying paper, please email me at the listed email address. So an overview of what I'll be covering is I'll actually explain what video background subtraction is. I'll talk about some of the different approaches that have been used and are currently being used. A non-exhaustive list, of course. I'll describe some of the experiments that I put forth. I'll talk about the results from particular algorithms that I experimented upon, and I'll conclude this presentation and talk about the potential for future work. So first things first, what is video background subtraction? So imagine, if you will, that you take a video sequence and you split each frame up into an individual image. Now what you want to actually do is take each of these frames and separate them out into two distinct images, one for the background and one for the foreground. And then what you do from that is then you take these two sequences of images and you make two separate videos. That way, if you were to play all three videos side by side, you'd get the foreground playing, the background playing, and then the combined ensemble. So a technique that has been more recently adopted to accomplish this is called robust PCA. And what that does is it's basically an extension of the classic principal component analysis, except that it allows for sparse noise to be placed on top of the data. One of the first works towards this was the principal component pursuit by Candes in 2009, and the objective function for this is listed below, where you are minimizing for both the L and S matrix the nuclear norm of the L matrix plus a regularized L1 matrix, L1 norm of the S matrix, where X would be your entire data matrix, and L is a low rank version with an additive sparse noise component, where S is the noise and it is sparse. So the different algorithms that have been used to pursue video background subtraction, first and foremost, there are several non-RPCA based methods, but listed here are just four that have been frequented earlier than later. I'll list them: the static frame difference methods, Gaussian mixture models, fuzzy models, and then you have neural networks and fuzzy neural networks. For the different models that incorporate the robust PCA, we have fast principal component pursuit by Rodriguez and Wahlberg, both Go decomposition and semi-soft Go decomposition are by Chinyi and Tao, and finally, the one that I'll be talking about is the reinforced robust principal component pursuit by Dr. Lee of the University of Florida. So the dataset that I used for experimentation came from the changedetection.net, specifically the 2014 database. I selected two of the baseline videos just to show the differences in the algorithms. I chose the highway and the pedestrian datasets, video sequences, and the two different types of experimentation that I did was just a basic runtime comparison and also the peak signal to noise ratio over the entire video sequence for each of the algorithms compared to the ground truth that is supplied with the changedetection.net. So this is the first part of the results. As you can see in the input images, that is a still frame from both of the video sequences, and you can see stacked three different algorithms: fast PCP, codec, and then the semi-soft codec. And from these representations, you can see that the foreground and the background was indeed separated, but what is not readily visible is how good these algorithms are comparatively, because it looks like they pretty much did the same job for both the highway and the pedestrian video sequence. So we'll get into this representation where we're actually looking at a hard thresholded version of all of the outputs and the actual ground truths. The reason to hard threshold the ground truths is because there are actual gray level representations within the ground truths, not just black and white, 0, 255. So doing the hard threshold forces it to being either 0 or 255 for comparisons. Since these algorithms don't output different amounts of gray levels, it's strictly binary valued. So as you can see in these, it's a little bit better to pick and choose where there are some differences. For instance, in the fast principal component pursuit, we can see that there's a little more of this bumper exposed than in these ones. There are some discontinuities in lines where you can see here. So it's a little better to see qualitatively, but let's talk about some quantitative measures. So as far as run times go, Godec ended up being the quickest in both of the algorithms, or sorry, both of the video sequences. And for peak signal to noise ratio, we actually see that the semi-soft Godec was the winner. There is unknown values for the R-squared PCP because it just so happened with the data sets that were used, it was computationally infeasible to run the experiments in any quick turnaround. It was taking several days to run, so I just forewent documenting those. So some of the problems that were encountered, obviously what I just said is that the data sets ended up being too large for the reinforced, robust principal component pursuit to actually be able to process it. Since we're dealing with a data set that is approximately 1700 frames, and each frame consists of a 320 by 420, 320 by 240 pixel image, so that ends up being quite large for this algorithm to encounter. Also, as far as the documentation goes, the semi-soft Godec version of the algorithm should have been approximately 4 times faster than the Godec, but that was not the case, and it was actually significantly slower. I suspect that the reason for that was because I used some pretty basic and standard settings when there could have been some parameters that were optimized for these particular data sets that would have allowed that algorithm to be faster. So now I'll show you the MATLAB simulation. So I went ahead and preloaded a lot of these matrices because it takes a good amount of time to construct them, but this is the code that would grab each image frame by frame and put it into the matrix for processing. And here's where it would actually run the algorithms and save the results. Okay, we'll go ahead and run this. Okay, now that the algorithm has completed running that section, we can see it's outputted some peak signal to noise ratio values. And here I will go ahead and run this section. This actually outputs the ground truth and the output of the foreground for both of the image sequences. And lastly, we want to plot everything side by side, the foreground and the background. And again, here we see the input image, and we can see that each one of the algorithms successfully split background and foreground. Now, for visualization's sake, keeping these in the same range allowed for better meshing, but to see the cars a little better, we could have changed the dynamic range of this independent of the background, and that could have potentially let us see it better, but I think it goes without saying that it successfully completed his task. And same for here. As we can see here, it's a little more difficult to distinguish the woman and the gentleman on the bicycle. But if we look at what we have here, we can distinctly see that the background and the foreground has been subtracted. And from the foreground after hard thresholding, we can see these images a lot better. Okay. So in conclusion, the robust principal component pursuit techniques that I've shown today are fast and effective. As I showed, they could take video sequences and separate the background and the foreground. Of the algorithms that I ran, the Go decomposition was the fastest, and the semi-soft Go decomposition was the most successful as far as the peak signal to noise ratio. However, I would like to see the R-squared PCP run just to see. I have a suspicion that it will perform the best. Definitely not in the quickest amount of runtime. There's optimization that needs to be done on that to allow for that to be computationally feasible. So for future work, I would like to incorporate more robust data sets for some of these algorithms and many more. By robust, I mean incorporating data sets that have dynamic backgrounds, for instance, where the background is moving a little more, like with a fountain, for instance, or moving water. Another robust data set would be if you take the video and you do panning, tilting, and zooming, so the background itself is actually changing. Actually performing a more exhaustive algorithm comparison would also be beneficial. However, there are many works that have rather extensively done this. I cited a few in my paper. And finally, I would love to find a more efficient solver for the R-squared PCP implementation. The basis is that it's doing optimization on a stifle manifold, and the solver that's being used for that is doing random projections in a very large matrix, since we're dealing with the data matrix where we have a background that's low rank and a foreground that's sparse. The orthogonal component to the low rank data matrix ends up being the rest of the rank that we're not considering that low rank, which ends up being rather intensive to do optimization over. So that concludes my presentation. I thank you for your time, and if you have any questions or concerns, please feel free to email me. Thank you.